Welcome back to the deep dive. We've been seeing some really striking advancements in large language models recently.
Yeah, especially how they reason, right? Things like math, coding.
Mhm.
It's quite impressive.
Exactly. And a lot of that seems to be driven by reinforcement learning, RL, applied after the main training, often using chain of thoughts.
Absolutely. You look at models like O1, DeepSeek R1, Kimi K1.5. They show this structured step-by-step thinking. It's a big step
It
up.
really is. And RL techniques are key to that.
They are. It helps fine-tune that reasoning process.
Okay, so let's get technical as always here. For this deep dive, we're focusing on two specific RL algorithms, direct preference optimization, DPO, and group relative policy optimization, GRPO.
Right. Two prominent methods for fine-tuning.
But here's a bit of a twist. We're not looking at them for language tasks today. Instead, we're examining how they apply to autoregressive image generation.
Which is a really interesting angle. These image models like Lamagen or Show Janus Pro,
hmm
they work sequentially, a bit like language models, actually.
Sequentially. So with images.
Well, they often use something called quantized autoencoders.
Yeah.
Basically, they break the image down into discrete tokens, sort of like words in a sentence.
Ah, okay. So you get a sequence of tokens representing the image.
Exactly. And the quality can be surprisingly good, sometimes on par with diffusion models.
hmm
This token representation lets us plug in DPO and GRPO loss mechanisms, just like with text.
Got it. So it's a good test bed for comparing these RL methods in a different but structurally similar domain.
Precisely.
So our mission today, really dig into the technical pros and cons, the scaling behavior of DPO versus GRPO for generating images from text prompts based on a recent study comparing them head to head.
Sounds good.
Let's start with the basics then. What are the core technical differences between DPO and GRPO we should keep in mind?
Okay, so DPO, it's become quite popular mainly because it's, well, efficient, less training time, less computational costs compared to some other RL approaches.
And it delivers results.
Oh yeah, it's shown substantial performance gains, especially for tasks needing maybe simpler chain of thought reasoning. We mentioned models like O1 benefiting from RL DPO is often part of that story.
Efficiency and good results for simpler stuff, but there have to be limitations, right?
Yes, definitely. DPO's effectiveness can sort of drop off with really complex reasoning
Why is that?
because it typically relies on a static, pre-collected data set of preferences. This output is better than that one. As the task gets more complex, that fixed data might not cover all the nuances, making it more susceptible to noise or biases in that original data.
Right. It only learns from the examples it's seen.
Exactly.
So how does GRPO tackle those more complex situations? What's its technical advantage?
GRPO is designed more for those intricate challenges needing complex QT reasoning. Its strength really lies in its iterative policy refinement.
Iterative refinement.
It uses self-generated data. During training, it generates outputs using its current policy, evaluates them, and learns from that. It's constantly updating based on its own performance.
Ah, so it's more adaptive.
Yeah, it can adapt better to complex task distributions because it's not just relying on that initial static data set. It explores more as it learns.
Okay, that sounds powerful. What's the catch? The technical trade-off for GRPO?
The big one is cost. Significantly higher computational costs, much longer training times.
And why is that?
It comes down to that online policy sampling. Continuously generating and evaluating data during training is just computationally demanding.
Got it. So a classic trade-off. DPO is faster, cheaper, good for simpler tasks, maybe less robust for complexity. GRPO is resource intensive, but potentially better for complex reasoning because it learns dynamically.
That's a good summary of the baseline difference, yeah.
Okay, let's see how this played out in the image generation study.
Mhm.
Starting with in-domain performance. How well did they do on tasks similar to what they were trained on?
So the researchers used T2I Comp for this, evaluating across several different reward models. These reward models are basically different ways to automatically score the quality of the generated image.
Right, judging image quality.
And interestingly, DPO generally came out on top in these in-domain tests, consistently across the different reward models.
Consistently better. That's quite telling for its strength within its training ground. How much better are we talking?
On average, DPO beat GRPO by about 11.53% in these evaluations.
Wow, okay. Over 11%.
Yeah. And in one specific case, using the T2I Comp official tools as the reward signal, DPO hit a peak improvement of 7.8% over GRPO. It really shows DPO's strength when the evaluation matches the training focus.
That's a clear win for DPO in domain, but the real test often comes when you go out of domain, right?
Mm,
What about generalization to new, unseen types of prompts or images?
exactly, and this is where the picture flips somewhat.
How so?
The study found GRPO tended to generalize better out of domain compared to DPO.
Ah, interesting. GRPO adapts better to novelty.
It seems that way. And another key finding was that DPO's generalization performance seemed more sensitive, more dependent on which reward model was used during training.
So how DPO performed on new images depended more heavily on exactly how its training preferences were defined.
That's right, they quantified this too. Using the Geneval dataset for out-of-domain testing, GRPO's performance range was tighter, around 1.81. DPO's range was wider, 2.72.
Wider range meaning more variability.
Yes, and the variance confirmed that. GRPO's variance was lower, 0.5486, than DPO's 0.9547. It suggests DPO's ability to generalize is more easily swayed by the specifics of the reward model it learned from.
Okay, so that highlights a really critical trade-off. DPO nails the stuff it knows. GRPO might handle surprises better, but DPO's handling of surprises depends a lot on its teacher, the reward model.
A very good way to put it.
You've mentioned these reward models a few times. Let's dig into those. What types did the study look at, technically speaking?
They explored three main types. First, human preference models. Think HPS image reward. These often use vision language models like CLA or BLIAP, trained on data sets of human judgments about aesthetics or prompt alignment.
So models trained to mimic what humans find appealing or accurate.
Essentially, yes. The second type was visual question answering, or VQA models. Unified reward and a fine-tuned ORM fell into this category.
How do those work?
They tend to use more powerful multimodal models like LFI that can understand image content more deeply and answer questions about it. They're trained on broad image text data requiring reasoning about the visual scene.
Okay, more detailed scene understanding. And the third type?
The third was metric rewards. These are more domain-specific tools. For T2I Compbench, each prompt focuses on a specific attribute, like color or object count. The metric reward just used the predefined evaluation tool for that specific attribute to score the image.
Very targeted evaluation then. So a mix of broad preference, deeper understanding, and specific metrics. The study also mentioned intrinsic generalization of reward models. What's that about?
Right, that was a neat part of the analysis. They basically asked, how well does the reward model itself generalize, separate from the RL algorithm?
How did they test that?
They used a best of n strategy. Generate n images for prompt, have the reward model score them all, and see how well that scoring aligns with good performance on the out-of-domain Geneval benchmark. This gave a measure of the reward model's own generalization power.
Clever. And what did they find? Which reward models generalize best intrinsically?
There was a clear ranking. Unified reward, the VQA type, showed the best intrinsic generalization. Then came image reward, human preference type, followed by HPS reward, another human preference type.
Okay, so the VQA model generalized best on its own. Did this connect back to the R algorithm's performance? Like, does a better generalizing reward model help the RL algo generalize better too?
That seems to be the key insight, yes. They saw that the performance rankings of these reward models, whether they were used with GRPO or DPO, generally lined up with their intrinsic generalization capability.
Wow.
It strongly suggests that the reward model's inherent ability to generalize is a major factor driving the generalization you get out of the RL training process itself.
So it's not just about DPO versus GRPO, but also crucially about the quality and generalization capability of the judge, the reward model.
Exactly. A better judge seems to lift both algorithms when it comes to handling new situations.
Fascinating. Okay, let's shift gears to the scaling strategies they tested. How did changing things like sample size or data size affect DPO and GRPO? Let's start with sample scaling.
Right. So for GRPO, scaling up the number of images sampled per prompt, the group size seemed to give pretty efficient gains in in-domain performance. More samples helped it perform better on things it was familiar with.
A fairly straightforward benefit for GRPO in domain. What about DPO?
DPO is more nuanced. Moderate sampling, like using maybe 8 samples to create preference pairs, some good, some bad, seemed to sharpen the contrast the model learned. This actually helped both in-domain and out-of-domain performance somewhat.
A sweet spot, then.
Kind of. But they found that excessive sampling, say using 16 samples, could introduce bias and potentially hurt generalization. So for DPO, just adding more samples wasn't automatically better. There was a balance.
Interesting trade-off there, too. What about scaling the amount of training data? More prompts, more image examples overall.
For GRPO, again, moderate scaling seemed best. Increasing the sampling size and the amount of in-domain data improved generalization up to a point. But too much data scaling risked overfitting GRPO to the training distribution, which hurt its ability to generalize.
Okay, so a risk of overfitting with too much data for GRPO and for DPO.
DPO actually benefited quite clearly from scaling the in-domain data. It boosted both its in-domain performance and its generalization.
Why would more data help DPO generalize better, given its reliance on static data?
The thinking is that more diverse in-domain data helps mitigate the biases that might come from a narrower set of preferences in a smaller data set. It gives DPO a broader view of what's good.
Makes sense.
And they were careful about how they scaled the data. They used GPT-4o to generate new prompts, ensuring they were semantically novel, and followed category constraints like generating new color prompts that were actually different, not just rewordings. They saw improvements doubling and tripling the data size.
That's a sophisticated way to ensure data quality during scaling. Okay, one last scaling dimension, iterative training. What did that involve?
They tried running the training in cycles. For GRPO ITER, after each round, they updated the reference model, the baseline policy used for comparison, to match the current policy. This keeps the KL penalty term aligned.
And for DPO ITER?
For DPO ITER, they resampled and reevaluated the preference pairs after each cycle, using the updated model's judgments, and also updated the reference model, so refining the preferences iteratively.
What was the impact of these iterative approaches?
The main observation was that iterative training seemed to push DPO's in-domain performance even higher, maximizing it. However, this often came at the cost of generalization, especially after several cycles.
So DPO got better and better at the training data, but potentially worse at handling new stuff.
It seemed that way. It suggests iterative training might lean towards overfitting the model to the specific preferences seen during training, even if those preferences are being reevaluated.
Okay, wow. We've definitely gone deep into the technical weeds here. To wrap this up, what are the main takeaways from this comparison of DPO and GRPO in the context of image generation?
Well, I think the big picture is DPO shines for in-domain performance and computational efficiency. It's fast and good at what it's trained for. GRPO, on the other hand, shows better out-of-domain generalization. It's more adaptable, but it comes with that higher computational cost.
And the reward model matters a lot.
Hugely. DPO's generalization is particularly sensitive to the reward model's quality and its own intrinsic generalization. And we saw that scaling strategies, samples, data iteration, they don't have simple effects. It's complex, with trade-offs between in-domain gains and generalization for both algorithms.
It really underscores the complexity of training these models effectively. This has been super insightful, thank you. It leaves us with a big question, doesn't it? Given these technical trade-offs, the influence of reward models, the nuances of scaling, what are the most promising paths forward for developing RL methods, especially if we want models that are not just high-performing but also generalize reliably?
That's the key question, isn't it? Finding that balance. There's clearly a lot more research needed to understand these interactions fully. For those of you listening who want to dive even deeper into the technical specifics, definitely check out the research paper we discussed.
We'll have a link on the webpage.
Yep. And keep checking the page for updates on AI and ML research. Thanks for tuning into this deep dive.
Thanks, everyone.